Hello, my name is Andre, and I am a second-year PhD student at the University of Cambridge. I will talk about a neat way to write concurrent programs in Haskell that are guaranteed to never deadlock. This is based on graded monads, and the idea behind this Perl came up when I was researching them in the context of various other program analyses. This functional Perl was co-written with my PhD supervisor, Alan Mycroft. A sometimes heard claim made by some members of the programming languages community is that functional programming is a good setting for writing parallel programs. Indeed, there is some evidence in support of this, with futures and promises finding their way into traditionally imperative settings, and MapReduce being a popular distributed computing paradigm. Outside of asynchronous and embarrassingly parallel programming, the evidence is much less clear. Haskell offers several ways we can turn to more explicit ways of doing concurrency. For example, using MVars, software transactional memory, or using foreign function interfaces. MVar synchronization is most similar to classical mutual exclusion locks, or binary semaphores. An MVar is an explicit synchronization variable used for communicating between concurrent threads. An MVar can store a value of some type A, and it is either empty when it stores nothing, or full when it stores a value of type A. An MVar is created using new MVar and new empty MVar constructs, which are read and written to using blocking take MVar and put MVar operations. There is a close connection between programming with MVars and the I/O monad, so MVar manipulating code can be intertwined with other I/O side effects. MVars are flexible and can be used to implement other concurrency primitives. However, not being careful can lead to deadlock, multiple threads waiting for other threads to release certain locks. An alternative is software transactional memory. Here, the programmer writes a transaction wrapped inside the STM monad. When some assumption is violated, the transaction is retried. Shared data is done using transaction variables, or TVARs, which are read from and written to using read TVAR and write TVAR, and they are created with new TVAR. This is similar to MVARs, but in the context of software transactional memory, and they exist within an STM block. Transactions are run using the atomically function and reset using retry. While software transactional memory gets rid of deadlock, there is no guarantee of progress. Transactions can keep retrying indefinitely. There is a well-known theoretical result in deadlock when it comes to mutual exclusion locks, and it's regarding lock order. Suppose a total order is assigned between locks. If a program obeys a structured ordering discipline, it is guaranteed not to deadlock. This structured locking means that if lock L1 comes before lock L2, then L1 should be acquired before L2 is, and L1 should be released after L2 gets released. The main motivation of this Perl is integrating this idea into the type system of Haskell. Can we write programs in Haskell that exploit this fact? And can we have the type checker explicitly reject programs that do not obey this ordering discipline? In this talk, I will present a framework for writing deadlock-free code. I will start by explaining the idea of graded monads, which are key for embedding the analysis into the type system. I will then present the operations used by the framework through some examples. Then I'm going to take a deep dive into the implementation, which mostly turns out to be simple and elegant. Finally, I will address some interesting issues that arise in practice and how to resolve them, namely how to handle some corner spots regarding Haskell type inference and how to add support for memory regions. All of the further details can be found in our paper. To recapitulate, a monad is a type constructor along with a return function and a bind function. They should satisfy two identity laws and one associativity law, and I don't show them here. They're probably familiar to most of you. Graded monads are a generalization of monads. The first necessary component is a grading algebra, which is a partially ordered monoid. A graded monad is first given by a family of annotated type constructors TR for all R in the grading algebra. As before, there is a bind operation, though now it is polymorphic in annotations as well as types. Notice how the bind operation combines the annotations given the two arguments, and it uses the multiplication operator of the grading algebra. There is also a return function, and the grade carried in the result is the identity element of the algebra. Finally, in addition to these operations, there is also a polymorphic explicit subtyping coercion function called sub. All of these components should satisfy laws analogous to those of monads, two identity laws and one associativity law, as well as an additional monotonicity property. And this is a Haskell type class representing graded monads. Here, M is a constructor that takes an element from the grading algebra D and a type. A graded monad first requires specifying this algebra, a unit element drawn from this algebra, a sequencing or multiplication operator for the grading algebra, as well as a subtyping relation. Next, we need a return function and a bind. And in addition, we need the type coercion function. In this particular signature, we add the other version of bind, the greater greater rather than greater greater equal, in order to change the behavior of Haskell's do notation if we use the rebindable syntax extension. We use a graded monad called sync. Its underlying algebra is that of lock sets, which are represented as type-level lists of strings. Alternative representations are possible, of course. With this string representation, the order assigned between the locks is lexicographic. There are two operators in locks. First, taking the union of two sets of locks, represented by this disjunction-like notation, and it is a type-level operator. The second one is a partial operator that adds a lock to a list, which is represented using the Haskell type class partial cons. More on that later. There are two main operations used for concurrency. The first is synchronization. The second is parallelism, run through threads in parallel. Synchronization is provided using functions specific to each lock. So there are functions such as syncx and syncr and syncy, all of them representing structured locking. If some expression M has type syncRA, meaning it makes use of lock set R, then syncx of M only type checks if X comes before all the locks in R, in which case its type just adds X to R, well, cons it to the beginning. This expression is just a computation that first acquires lock X, then it evaluates M and stores the result in some temporally variable R, and then it releases X and finally returns R. In monadic style, this is written in the following way as shown in the slides. Now, parallelism is much simpler. Given two threads wrapped inside the sync graded monad, you just run them in parallel. The thing that you return is actually a pair of the things the two threads evaluate to. Let's look at a few examples. Firstly, we're able to lift writing to standard output and waiting to the level of sync using lift.io. And we can call these two lifted functions sync put string line and delay. We can use this lifted printing to write a program in which two concurrent threads print to standard output. One outputs thread 1, the other outputs thread 2. However, these two threads might interleave and output something garbled to the output. If both of these threads are wrapped inside a syncx. Then they're executed in a serial order. Either first one goes first or the second one goes first. The next example is that of two concurrent threads which does not type check due to possible deadlock. There is a violation of the lock order discipline. In one, x is acquired before y, and the other thread, y is acquired before x. Finally, we see an example of two threads that use locks x, y, and z, and they obey the lock order. There is the classic dining philosophers problem. Suppose 5 philosophers are seated at a round table, and during the course of the dinner, they eat, talk, and think. To eat, they need to access both the fork to their left and the fork to their right. How do we program these philosophers so that they don't end up in a deadlock situation? The simplest solution is acquire fork to my left, acquire fork to my right, eat, release right fork, release left fork. However, it is possible that immediately all 5 philosophers will take the forks to their left, but now they're stuck. This is a simple example of not obeying the ordering discipline. So we need to impose some kind of order between the acquisition of forks. Our framework allows us to see how this is implemented in action. We want to write terms philosopher 1 up to philosopher 5, which we then run in parallel. Assuming we're working with locks v, w, x, y, and z, philosophers can be implemented using the pattern seen for philosopher 1 here on the slide. That is, we first have a synchronization on the lock v, then we state that we've acquired the first fork, then we have another set of instructions wrapped inside the synchronization on lock w, then we print to the standard output, and finally we return. When after this is returning, this is the end of the sync w block, so this is when the unlocking of w happens and also the release of the lock v. And if all of them follow this pattern, it's very obvious what philosopher 1 up to philosopher 5 implementation should be. It all comes down to the implementation of philosopher 5. If philosopher 5 first acquires the lock z, that is the fork to their left, and then lock v, then the 5 concurrent threads may deadlock. Hence, the type system should explicitly reject the program. On the other hand, if v is acquired before z, then the code is guaranteed to be deadlock-free. On an implementation note, we don't need to write 5 separate implementations. One way to prevent code duplication in this case is to write a generic philosopher function that takes synchronization functions as arguments. The resulting code is short. It does not require any additional type annotations to have the types inferred. Then, functions philosopher 1 through philosopher 5 can be implemented in terms of the philosopher function and passing the appropriate synchronization functions. The type system manages to infer the type for a philosopher, shown on the bottom of the slide. It doesn't explicitly expect synchronization functions, but they fit the type requirements easily. Let's finally turn to how this works under the hood. First, it is necessary to define the grading algebra. We use the data-kinds Haskell extension to implement type-level lock sets. As said before, the lock sets are represented as sorted lists. The merge or multiplication operator is implemented using type families. The implementation is the typical merge 2 sorted lists into one sorted list, as seen in merge sort, except now it's at the type level. So we have 2 trivial base cases, when one of the arguments is an empty list, and the inductive case, in which case the heads of the list are compared, and the 3 different results of this comparison are handled accordingly. This is the merge operator seen in the parallelism operator. The other important operator is the one seen in synchronization functions. Given that we want it to be partial, a simple way to implement it is using type classes that carry a functional dependency. Partial cons, x, x's, y's, represents the fact that y's is just x added to x's, but only when lock x comes before all the locks listed in x's. Otherwise, it should just not match any partial cons x, x's, y's. This is written in the way shown on the bottom of the slide. I don't show the definition of less than all. It is not very difficult. There are a few other things that are necessary for completion, and you can see the details in our paper. With this, we can define the actual sync-graded monad. The core idea is that the sync-graded monad should have access to all the necessary locks. Locks are represented as MVars that carry a unit value. No data. They're just a mutex lock that is either full or empty, representing whether it's been acquired or not. Given that sync performs I/O action, the I/O monad should appear in its definition. The underlying representation of sync is just as a mapping from a list of unit-valued MVars to an I/O computation. This proves to be just appropriate for our setting and might rightfully invoke comparisons with the reader monad. More on that later. It is unsurprising that sync is an instance of a graded monad, which can be implemented as follows. The code showing that it is an instance of a graded monad is not very difficult. The unit element is just the empty set or the empty list. Sequencing is given by the merge operation. Subtyping or subaffecting is given by sublist, which I didn't show previously, but it isn't difficult to implement. The bind operation is just using the internal bind of I/O, but wrapping it inside of the sync monad. And sub is just a simple case of wrapping and unwrapping. You will notice that the grade has no clear semantic link with the terms that it represents. It's merely an annotation for the analysis. Showing that all the graded monad laws hold, well, they only rely on I/O being a monad, which is true. Showing monotonicity is a separate exercise, but none of this is difficult to show. To implement synchronization, that is the sync functions, we first want to implement the explicit locking and unlocking functions. These should be hidden or not used by the programmer, otherwise they just mess things up. When thinking about what sync is, the implementations are unsurprising. They are just take MVar and put MVar lifted to the level of sync using the appropriate constructor. These functions can be then used to implement a create sync function that creates all of the sync x, sync y, and so on, according to the recipe we mentioned earlier. Acquire a lock, perform the operation, and tie the result to a temporary variable, release the lock, return the result. Finally, the synchronization functions explicitly state the partial cons constraints, like in the syncx code as shown on the slide. Parallelism implementation is slightly different, but still relies on using MVar operations. Two temporary MVars are introduced to store the results of the two concurrent threads that are then run in parallel. There is some stuff that needs to be added to these threads, namely taking the final result and writing it to these MVars. These temporary MVars are then used to await for these threads to finish before the final result of running them in parallel is evaluated. We have to do some lift I/O magic in order to put the MVar operations into the sync level, but it is really nothing surprising. In this example, I use do notation, and here I am assuming that rebindable syntax is already being used, so all of the hidden bind operations are actually the graded versions and not the usual monad binds. There are a few things that are explored in detail in the paper that I just want to give you a taste of in this talk. Firstly, the mutual exclusion locks do not synchronize on data or allow sharing data between threads. We can change this, and it isn't too difficult. The simple underlying representation of sync we've seen before resembles that of the reader monad, and we can exploit this. Rather than using MVars over unit values, the MVars can store values of other types as well. This means that all shared data is protected by a lock. To use this kind of heterogeneous list, we just turn to a stack of monad transformers, though other approaches are also possible. We first define a monad transformer lock-t, which takes a type of data to synchronize on and a monad, and builds a new monad on top. The internal representation of the sync-graded monad is then analogous to what we already had. The resulting framework looks a little like using a monitor, but without the full power of wait and notify that is seen in languages like Java. You can see implementation details of other operations in our paper. They're not too difficult. Handling recursion requires some additional effort. Consider the following iterated bind operation, binding n times the same action m. It can be concisely written using a fold functional. If we just write it like this and use it, we get issues with type inference. Performing an action with the same set of locks several times should not change the set of locks, but Haskell on its own cannot infer the simplification is sound. Just writing the type explicitly to the type checker isn't sufficient either. Instead, we have to use this type idempotent R, which is just an equality type. It tells us that R merged with R just gives you R back again. We can use it as a constraint in all functions to trial the idempotence property, like in repeat bind, and that's it. We can now use repeat bind in many settings and aid the type inference algorithm. And whenever we need any other properties in order for type inference to pass, we just write them down as other kinds of constraints. While this talk is about our functional Perl, there are some ideas regarding future research, some which I'm exploring right now as part of my PhD. The first extension is an obvious one. Why should a programmer introduce an explicit total order? Couldn't the type inference algorithm or the algebra infer that as well? Well, yes, it can. Furthermore, a partial order is sufficient. This also allows us to have a different order at different points in the program. You can have a thread in which x is acquired before y, and another in which y is acquired before x, but because they never run concurrently, it's completely safe. I have done some preliminary work on this, and the best solution I find in Haskell is somewhat expensive when it comes to compile time complexity, and they come with some additional difficulties. Staying on the topic of concurrency, we can look into using different concurrency primitives and using grading to guarantee correctness. These could be constructs such as explicit binary semaphores or monitors. However, more generally, is there a way of encoding many interesting static analyses by a Haskell-like type system using grading? This is what I'm exploring for my PhD thesis. For a lot of analyses, the Haskell type system is sufficient, which is the reason why I'm giving this talk. There are trouble spots when it comes to more sophisticated analyses. A common difficulty is the lack of Beckeri recursive types in Haskell when it comes to full inference. This is especially relevant for recursive programs. What I talked about was how a rather simple graded monad can be used to program with some fairly constrained concurrency primitives, and that the resulting programs are guaranteed to be deadlock-free. Deadlock freedom is based on the existence of a total order between locks. In doing so, we used a few Haskell extensions, mostly regarding type-level operators and data kinds. However, there is no need for the full extension of dependent types. In a lot of cases, we get types inferred with minimal programmer intervention. I hope you found this topic interesting. Thank you very much.